Hello, everyone. Welcome back to the Development Research and Practice course. During this week, we will discuss Chapter 6 of the handbook, Constructing and Analyzing Research Data. But as people trickle in, I would like to first do some housekeeping announcements as usual. So first of all links related to course materials, quizzes, reading lists, application questions can be found in the link bit.ly/drip overview. Avnish will also share this link in the chat. We share the materials at the beginning of every week. And please remember to keep your participant ID safe. Make sure you are using the correct ID to submit your quizzes. This is how we can connect you to your information. All the quizzes have only one common deadline. You need to submit all the quizzes by September 1st at 11:59 our time, so Eastern Daylight Time. If you have already submitted some quizzes, you can track your progress using our tracker, and this is at the bit.ly/drip tracker link that Avnish is also sharing in the chat. Okay, so let's get into our book chapter. So in this chapter, we are going to discuss two key steps in research data work: the construction and the analysis of data. These two tasks are described in the same chapter because they involve translating research decisions into code, although the nature of these research decisions are different. So the nature of the research decisions involved in construction and those involved in analysis are different. So we don't have time to cover every single thing that we mentioned in the chapter. So what I'm going to do today is that I'm going to take you through what I think are the most important aspects of this chapter and some things that I want to highlight so that you can understand why this chapter is necessary. One important note to make is that we will focus on how to organize the workflow to implement the research decisions rather than on how to make research decisions. There are several resources that focus on research methods, and this is not what our book does. What our book is trying to do is to fill in the gap of making sure that everyone is prepared to actually implement them in practice. That's the in practice part of the book title. So when conducting data construction and data analysis, it is very common for researchers to be so focused on the results that they are seeing that they don't develop a systematic approach to how to organize the code and then documentation as they create them. So what this chapter will do is provide a workflow to implement these tasks. And as I mentioned, we will focus a lot on what are the most error-prone tasks and how thinking about them in advance will help you avoid these mistakes. So the reason why this chapter is important is that you do not have time for an ad hoc approach to data analysis. If you are always doing things without thinking a lot about what you're doing, this may seem like it's saving you time, but as we'll see over and over, you will see this motive a lot over this presentation. In the end, you will spend more time overall your project workflow if you are trying to do each of the steps very quickly. And this chapter is divided into 4 sections. The first one is on data construction, the second one on data analysis, the third one on creating research outputs, and the fourth one on using dynamic documents. You see that this presentation is particularly focused on construction, And this is because construction is where mistakes are most likely to happen. Data analysis can be extremely complex, but the methods behind data analysis are the main source of complexity. Once you have made your research decisions, writing code to implement them is easy if you have organized your data work well. So what does that mean? If you follow the workflow that we outline in this chapter, then writing analysis code is easy. And this is because statistical software already have off-the-shelf commands that implement most quantitative analysis designs. If your data is in the right format, then using them is straightforward. However, if you're having a lot of problem to actually use the off-the-shelf commands, that probably means that your data has not been processed in such a way that when you get to analysis, it is ready to be analyzed in statistical software. So what we'll focus on today is making sure that you can get to this point where when you're ready to do data analysis, your data set is also ready to be analyzed. Okay, so the first thing that we're going to talk about, as I mentioned, and the main thing that we'll talk about today is data construction. This is how we call the process of going from clean data, that data that we observed, from the world, and then we start to abstract this data so that it can represent the concepts and outcomes that we are studying in our research. There are two inputs that are always needed for data construction. The first one of them is the clean data set, and this is what we discussed on the last chapter. So the clean data set should have been created following those guidelines. So it can be formed by one or multiple tidy data tables. It has been validated through data quality monitoring, and corrections have been incorporated. I'm gonna ask, okay, sorry, I don't think I've made the other authors of the book co-hosts. You are co-hosts now. Please make sure that the chat is closed so that we only receive questions through Q&A. And for everyone, please use Q&A to ask questions so that we can track when they have been answered or not. Okay, so the first input for construction is the clean data set. The second input from construction is, of course, the research design that we are trying to implement. For construction in particular, the research design inputs that we need are the list of indicators required for analysis, the definition of those indicators, so you need to know what variables you are trying to create, and the data flow chart that we have discussed in chapter 3. So we have already thought about the process of construction before getting to it. We already have a map of what we need to do. So the data flow chart already includes the key steps for data construction. And if you created it according to our recommendation, then you know exactly what are the different analysis data tables that you want to create and what are the steps that you need to take to create each of them. The output of construction is therefore the analysis data set. And what is that? The analysis data set is made of one or multiple purpose-built analysis data tables. So let's take this definition apart and understand what each of these points mean. So why does it contain multiple, or why can it contain multiple data tables? Because when we get to analysis, we stop thinking about the unit of observation, that is, the level at which we actually measured stuff, and we start thinking about the unit of analysis, which is the level that actually matters for our research design. For example, if we are doing a evaluation of a policy that was randomized across schools, we may have observed test scores for each individual student in those schools. But what we are interested in is analyzing the effect of the policy at the school level, because this is the level at which the policy was delivered. So we will be probably analyzing the results at the school level. That means that we'll be looking at the average test scores per school. So this is an example where the unit of observation, a student, is different from the unit of analysis, which is a school. Before we can get to the data set at the school level, we'll start from different data sets or different data tables at different levels. So we may have a data table at student level, a data table at teacher level, one at school level, and then we will organize them until we get to a unit of analysis during data construction. And we may also, in the end, have different analyses that need to be run in different levels of observation. So in our data tables, in each of these analysis data tables 1, 2, and 3, each row will represent one instance of the unit of analysis. So in a school level data table, we'll have school 1, school 2, school 3, and in the student level data table, we would have the different students in each of these schools represented in one row. And since our research design may include more than one unit of analysis, then we'll need more than one analysis data tables. So okay, this is where I wanted to get. Note here that we will only keep in the analysis data sets the variables that are actually relevant for our analysis. And this is because we want the analysis data set to be very digestible. We want it to be easy to understand, and we want it to be quick to read. And since you may need to include variables that were originally observed at different levels, if you remember our discussion about tidy data from last week, you will notice that these analysis data sets do not need to be tidy. And this is something that came up in a question last week. So analysis data set may have variables that are repeated, whose values are repeated over a lot of lines. So for example, if you have a student level data set, but you are controlling for school characteristics, then you'll have different characteristics of the same school over multiple rows for each student that is part of that school. What we will not have is one variable that's spread over multiple columns. And of course, because we want our analysis data set to be easily digestible, we will do our best to make sure that it is very well documented. So as you go through data analysis, make sure that you are documenting each of the steps taken so that other researchers can retrace them and also understand the research decisions that they are representing. There are 3 pieces of documentation in particular that should always be included in any project, regardless of your research question. I just realized that I forgot to turn on the legends earlier, so I'm doing that now. Sorry, subtitles is the word in English for legends. Legends is the Portuguese word. Okay, so there are 3 pieces of documentation that should always be included in any project. The first one is the code book that is summarizing the details of the data set through descriptive statistics and metadata. So we discussed what a code book is last week for the clean data set. That's the same thing that you want to include in your construction data set. You want people to be able to see what are the high level idea of the values of each variable. And just like we discussed last week, we also need a data dictionary. So this is a list of all the variables in our data set and their definitions. The data dictionary, as someone asked last week, may be part of exactly the same document of the codebook, or they may be created separately. But these are 2 pieces of information that we need. What are the definition of the variables and what are the values that they contain? And finally, we also want to make sure that our code is well commented, so that the research decisions that we are implementing can not only be inferred by the code that we've written, but they are also described in plain English or whatever language your project is using in the same document. And this is because ideally we will minimize the number of different places that we need to look at to understand our data. So if you need to open the code and also have, a methodological note open and a code book open and a data dictionary open, and look through these different places to understand what you are reading, then it can become a little cumbersome to actually understand the code. Now, another thing to keep in mind when we are writing construction code is, yes, that it needs to be very well documented, but also that it needs to be organized separately from the data cleaning code. So as we discussed last week, the first reason why we treat construction and cleaning separately is that cleaning is only making changes to the format of the data, and the clean data set reflects the reality as originally observed and measured, while the analysis data set incorporates research decisions to these observations, creating measures of more abstract concepts and variables that can be directly used for analysis. So when we are writing code, we want to have these 2 things separate, so we can easily identify what is a research decision and what is just a matter of which software you are using. So here's an example. If you have a clean data set, it may include information about the quantities sold by a firm and the prices that it charged. These are the information that you observe directly. But when you're running analysis, you may use these 2 variables to create a new variable, which is the sales revenues, even if the sales revenues were not originally observed in the data set or when you first acquired the information. So main difference is what you observed versus what you are abstracting or what you are creating for research purposes. And a more practical reason for writing data cleaning code separately from data construction code is that data cleaning code is very specific to each original data set. This is what we are seeing here. In general, each original dataset will have very particular cleaning needs because they will contain different information that was originally acquired in different formats. So using the script that you wrote to clean one data set in another data set will probably result in errors. However, I can't seem to go to the next slide. Okay, however, when you are creating indicators, when you're constructing the variables that you use for analysis, you want to make sure that the variables are treated and defined consistently in all data sets. And this is very important for your analysis. So let's go again to an example. Let's say you have a project that collected 2 rounds of data, a baseline survey and an endline survey. Unless the 2 data collection instruments are exactly the same, which is very uncommon, they will need to be cleaned separately because they will have very specific data cleaning needs. On the other hand, the analysis indicators that we want to create from these 2 should be consistent across both rounds so they can be analyzed and in a comparable manner. So we want to analyze them together. We want the indicators for each round to be comparable. So in the example we discussed before, where we have revenues being created from sales and prices, we want to make sure, for example, that we have treated outliers in exactly the same way across the 2 rounds. And then if we did any imputation of missing values, that we use the same method. So our results are not driven by the difference in how the indicators were defined across the 2 rounds. So what does that mean? It means that we will need separate data cleaning scripts, as we have here, but when we're constructing the indicators, we'll actually do that together for all the different data sets. So we'll first combine them so that we can have only one construction script, making sure that if a change is made to how you define an indicator, this change can easily be applied to all rounds at once. And if it's not yet clear for you how come construction and cleaning are different, we can now take a look at the different tasks involved in construction, and hopefully it will become clear. Okay. The first construction task that I want to talk about is handling different units of observation. When research involves different units of observation, creating data analysis data tables will probably mean combining variables that were measured at each of these different levels, like we discussed earlier in the school evaluation, the school program evaluation. To make sure that analysis variables are consistent across the data sets, each indicator should be constructed in the data table of the unit of observation of the original measure. That's very complicated. But basically what it means is that if you observed something at one unit of observation, then the derived measure for that something should be calculated at the same unit of observation. Once you have done that, you may use this constructed variable to aggregate it and carry it over to other units of observation. Here is an example of what that means in practice. sorry, I seem to be having some trouble just passing slides. Okay, that's better. So let's say we have a project that is collecting data about farmers. The unit of analysis is the household where farmers live, but you also collected information about each of the plots owned by those farmers. And what you want to do now is to include a variable in the household level data that shows the total land holding for the people in one household. How do you do that? Well, you will start with the plot level data. This data will contain the plot ID. It will also link the plot to a household through the household ID that owns that plot. And it will contain information about the size of each of the plots in the data. So what you're going to do is that you're going to create a new variable in this data set that standardizes the plot size. So let's say that some people reported the plot size in square meters, some people reported their plot sizes in square feet. You need to make sure that these are all measured in the same units so that you can analyze them together. So you will create this variable at the plot level and make sure that all the plot sizes are measured in hectares. What you can do now is that you can aggregate the observations to the household level, adding the sizes of all plots that belong to the same household. Note here that both the number of observations and the number of variables in the resulting data set has decreased. This is because you no longer have a plot ID, because this is not a household level information, and you no longer have the originally reported plot size because they are reported in different units and they cannot be aggregated. Another very common and also very error-prone data construction task is to combine data tables. So instead of just simplifying them, let's say what you did here, now that you have this household level data, you can combine it with other household level data that is already in your data set. So we often need information that was originally acquired at different units of observation or over different points in time. And combining information most often involves two types of operations. The first one is what we call appending data. This means combining data tables by stacking them on top of one another. And by doing so, we are adding new observations to the resulting table. This is done when you have different instances of your unit of analysis in each of the tables. So the two tables will have different observations, but the same unit of observation. So for example, when you're creating a panel data set at the country and year level, by combining different data sets that have the same countries, but different points in time. So the appended data set should ideally include all the same variables, or otherwise it will be tricky to analyze the resulting data set because you have a very large number of missings if a variable was only included in one of them. Additionally, it is important to make sure that the data sets are harmonized before doing this. What does that mean? That means that columns representing the same variables should have the same name, that they should be measured at the same units, and that their categories levels should match. So we actually have created a command as part of our IE field kit package that's called IE Codebook Append, and that is meant to facilitate the processing of harmonizing data sets. Now, another thing that you may want to do is to combine data sets that include the same instance of the unit of analysis, but that have different variables. That would be the case when you have the household level information that you created from aggregating plot level variables. And now you want to combine that, you want to add that to the rest of your household level information so that you can actually analyze it. So to do so, what you're going to do is what we call a merge operation. By doing that, you combine two different data tables that have the same ID variable, and you bring columns from one data table to another. This means that the commands that implements this operation in statistical software is actually very complex, because when you do a merge, you do not necessarily maintain all the rows and columns of the data sets being combined, and sometimes you don't even want to do that. So when you are writing code to implement merge operations, you need to know very well the command that you are using, or you may end up with a different result than you originally intended. But fortunately, we have a few tips on how to do this so that you can avoid errors. And they mostly involve thinking about what you want to do in advance. So whenever you're doing a merge, you need to think first, how many observations will be matched? How many do you expect to not match, and why? So if you don't have information, for some people, because they refuse to tell you the size of their plots, you will not be able to match that to the household level information. And then you want to think about what you want to do once you combine them. Do you want to keep observations that didn't match? Do you want to remove them? Do you want to only keep informations that did not match? And finally, when you actually get to write the code that implements this, you want to check that the result matches your expectations and what you intended to do in your analysis. Okay, I have one last construction task to discuss, and then we can stop a little bit for questions. The last construction task is one that is almost always necessary, no matter what kind of data you are receiving. And it's called creating analysis variables or constructing analysis variables. What it means is that we're taking variables in the clean data set and transforming them in some way so they can be used for analysis. And we actually already talked about this when we talked about creating a revenue variable or standardizing the units that we use to measure our plot size. So these are two different examples of how you can construct variables. So you may combine two or more variables into one indicator, like the revenue case. And when you're doing so, you need to be mindful of their units and scales so they can be measured. They are measuring the same thing before they are combined. And the same thing is true both for numeric or categorical variables. But even if you're not combining variables, you may still need to make adjustments to your original observations so that you can make meaningful analysis on them. So that's the example that we saw on plots. We need all plots to be measured on the same unit on our analysis data set so that we can analyze them together. And two other common examples is when you have a lot of missing values, you may want to impute values to observations that are missing, or you may want to treat outliers so that they don't bias your analysis. Now, how exactly these two things will be done, for example, imputations and outlier treatment, the method that you use to do that is a research question, and we are not here to answer it. But I do want to emphasize one thing that is related to how you implement this, is that new variables should be created when you are doing this. So instead of replacing your original variable with the imputed variables, with the imputed values, sorry, what you want to do is you want to create a new variable that will be just like it's displayed here. So you have one old variable and a new version of it, because this will allow you to run analysis on both of them and see how your research decisions affect your result. Okay. Break now. I'm going to drink some water and let you ask some questions. We are done with construction, which, as I mentioned, is the most complicated part of this presentation. So I'm sure that you have a lot of questions. Please go ahead and ask them. You are very quiet today. We have not had any questions yet. I hope this is because I'm being very clear and not because you don't understand anything. Okay, we have a question now. How could you go about merging many to many? And we also have someone saying that my explanation is very clear. Thank you. So how do you go about merging many to many? This is definitely the most error-prone version of merging. You need to think very carefully about what you are trying to do and about why you want to merge many to many. In general, you do not want to do that, to be honest. But there are, so again, the implementation part of this is very easy. There are commands in both R and Stata that allow you to do that, but you do want to go through the same steps. So think about how many observations should be merged and which observations should be merged from one data set to the next. And be very sure that you know how many observations you expect to have in the resulting data set, because otherwise you can lose control over it very quickly. It is very tricky to convert nominal to real values, for instance, in dealing with price data. Do you have suggestions on a good workflow for this? Yes, so ideally you would document the source that you use for your conversion rates. You want to make sure that you know what they are and that you note when you got these values. And ideally what you want to do is you want to create a separate data set that contains the conversion rates, and then you will merge that data set into your original data set, and then just multiply the values by the conversion rates. But it's very important that you document how you got the conversion rates and where you got them from. Okay, another question, very good question. Can I give the new data set a new name since it's no longer original? Absolutely, you should do that. You should save it as a separate data set, not save it over the clean data, and you should name it very clearly so that you know that this data set is the one that includes all the constructed variables, that this is your analysis data set, the one that you want to run your analysis scripts on. Does this process you have just explained apply when secondary data are to be used for analysis? Absolutely. The process is exactly the same. Another very good question, removing outliers and missing value imputation is part of data construction. Yes, when you do this, this is your research decision that you are implementing in your data. This is not what you observed. So you're absolutely correct. This is a construction task. Okay, I'm gonna move ahead now and I'll let my colleagues answer the next few questions. And if I have time at the end of the presentation, I'll come back to them. Okay, so let's go and talk about writing analysis code now. So when you get to this point, you have all the data at the unit of analysis, and it contains the relevant indicators that you want to study. And you can finally get to the point where you're going to get some answers to your research questions. So during data analysis, what we're going to do is going to implement quantitative methods, and quantitative methods in this case, because that's what this course is about. So we're going to implement quantitative methods to describe our data and to make inferences from it. As I mentioned in the motivation lecture for this chapter, construction and analysis turn the clean data. This is the clean data here, if you remember, the little Legos. And we're going to turn this into meaningful analysis outputs, so the interpretable outputs. What exactly those are like tables and graphs and maps, which we're going to discuss right now. But before I do that, I just want to make a clear vocabulary distinction. I will refer to tables and graphs for this presentation as outputs. But what I mean when I say that is raw outputs. So these are individual exhibits that will then be compiled into what we call final outputs, which is your report or paper that Ben is going to talk to you about next week. So you can see from the way that we organize this chapter that analysis and construction are separate and different tasks. In the research workflow, variable construction precedes data analysis because the derivative variables that we created in the analysis dataset need to be there before we can start writing our analysis code. So they should be coded into separate scripts to make sure that the indicators are consistent. If every time that you are writing a regression, you start by creating all the variables that you need, you may create the same variable in two different points in your code. And whenever you want to change how this variable is created, you need to change it in two different parts of your code. This makes the code very hard to maintain and increases the chances that at least one script will have a different sample or variable definition than the rest of them. However, it is true that in practice, we often write data analysis and construction at the same point in time, because as you're writing some analysis, you find something that you need to change in your construction. But even if you're doing that, you want to have the two scripts open at the same time and make the modifications to the right script. So if you need to change the level at which you are considering an observation and outlier, you're going to go back, going to open your construction script and make changes in there. And during the data analysis process, basically what you're going to do is that you're going to write a lot of code, and then you're going to rewrite it. You're going to go back to it, you're going to polish, simplify, and reduce your code. So you can think of analysis as a two-stage process. In the first stage that we call exploratory analysis, you will probably create a lot of statistics and try a few different models. Exploratory analysis is very often written as a flow of consciousness, since new ideas come up every time you see a new result. And that may not be the case for projects that have a P-analysis plan, because it's already very clear what are the analysis that you can run. But the point here is that when you're doing exploratory analysis, you are not creating very polished, custom formatted outputs, because these are only for internal consumption. And your team already knows the study well, so you can understand the results without a very compelling visual narrative. But as you advance and start to identify your main results, you want to pick the most relevant pieces you created during exploratory analysis, and organize, simplify, and polish the code that creates those pieces. So as your results start to shape a story, you'll be able to select which exactly are those tables and graphs. And the code for each of these exhibits should be extensively commented and reworked multiple times, so that when someone is reading your final replication package, they can understand what you're doing. Remember that formatting tables and graphs to look exactly like you want them to look is a very time-consuming process. So don't spend a lot of time doing this until you know that you will use a table or graph in your final output. So how do we implement these two stages in practice? Well, we want the code to be independent and from any other code in your project, except for the master data set, whenever it's creating a final analysis output. So you'll start from a fresh workspace, load the relevant analysis data, you will comment it a lot, and you'll end it by exporting a reproducible output. We'll talk a lot more about reproducible outputs in a little bit, but I just want to highlight now that just like we just talked for the analysis data sets, the analysis scripts should also have a very descriptive name. So if you want to find the code where you created one particular table, you can do that as easily as reading the script's names. Okay, so I just mentioned that analysis scripts end by creating reproducible outputs, but what does that mean exactly? In short, reproducible outputs are outputs that can be easily recreated and visualized. So they are exported from the statistical software in an accessible format that anyone in your team can open. Think PNGs or PDF for images, and CSV or TXT or TEC for tables. They do not require any manual formatting after they are exported, and we'll talk a little bit more about this in a minute. They have a version control system, so you can easily identify when your tables and graphs are changing, when your results are changing due to something in your data or your code, and they should also be descriptively named. See that there's a pattern here where we talk a lot about being able to identify data, code, outputs, and track and link them to one another quickly. So the most important lesson I want you to learn from talking about reproducible tables and graphs is that the ideal analysis workflow does not require any manual formatting. You may think that making changes to tables and graphs manually is faster than figuring out how to implement those changes in code, but tables and graphs for the same project will usually have the same formatting. And as the number of outputs in your project increases, it becomes easier to just adjust one code for multiple outputs than to edit each of them manually. And although you may think that you will only need to do this once for each table and graph, I promise you will not. At some point, you will need to make changes to your analysis and you will need to update your outputs quickly. So making this in a reproducible manner is your best choice. There's one last takeaway that I want to discuss with you before I open for questions again, and that is that the ideal analysis workflow also does not require any copying and pasting. So we're talking here about reproducibility and about automating your workflow. And when it comes to copy and pasting, this means that you should never copy results from Excel to Word as you're writing a report. Because if you simply forget to copy paste one line, you may spend a lot of time interpreting the results that are not actually the latest results. You should also never copy paste results from a software console to Word or Excel. This has the same problem and also is completely unnecessary. All modern statistical software have commands that allow you to export outputs into a commonly accessible format in one line. And here again, you may think that copying and pasting is faster than figuring out how to use these commands, but the amount of work needed in a copy-paste workflow increases also very rapidly with the number of tables and figures included in a research output. And so do the chances of having the wrong version of a result in a paper or report. Again, you may also think that, well, we'll only need to copy paste it once, but no. At some point, you will think that you have the final output ready and you will not have it, and you will want to make some changes to the colors you're using or even to your analysis. So make sure that you set up a reproducible workflow. And there's one easy way to do this, which is dynamic documents. There are a bunch of different options to use them that depend on how familiar you are with statistical software and with tools such as LaTeX. And even if you do not want to learn how to code in Markdown or LaTeX, you can still use something like Dropbox Paper, at least for the exploratory analysis phase. Unfortunately, I have gone too slow over this presentation, so I will not get the time to talk about each of these things in details, but hopefully we'll have some questions and then I can discuss whatever you think is most relevant now. I know we have implementation questions already for you in OSF, but these for me are the most important of them. So basically, if you need to pick implementation questions to really focus on, you have a list here. Thank you. Sorry I was too slow on this, but I'll be around to answer questions for as long as we have them. I'm just, as questions start coming up, I will let, I'm gonna look at the already answered questions and see if there's anything that I want to bring up with everyone. So we have one question here asking whether the difference between appending and merging is just that for appending you need to harmonize data sets first and not when merging. That is not incorrect, but this is not the only difference, as Ben has already shown. But I think this figure here is. Am I still sharing my screen? I am not. The figure in the presentation makes this much clearer, which is here. Okay. When appending, when you're appending to data sets, you are increasing the number of columns, of rows, I'm sorry, so you're increasing the number of rows that you have in the two data sets. So the resulting data set will have more rows than each of the combined data sets. And when you are merging, instead of adding more rows, you're going to add more columns. So I think this is an easier way to think about this process. Another very good question, can variable construction be adjusted at the stage of data analysis? Absolutely. It can, and 99% of the projects will need to do that. And that's totally fine. There are things that are a lot of mistakes, for example, that you don't notice until you're at the analysis stage, and you can go back and adjust the construction. That's totally fine. But as I said, remember to have, two separate scripts for it, so that you can make the adjustments in the construction code and not directly in the analysis code. Another question here, is there any particular Stata commands you recommend for exporting results? Yes, there are a lot. I see that Ben is already replying, but we actually have a whole section on how to export tables from Stata. We also have some code and some templates that you can use. I'm sure Ben will share them in the Q&As. Okay, next one. This is not really a question, but I have come across scripts where researchers combine data cleaning and variable construction. You made a great point as to why the two should be separate. Thank you, Janet. I have also come across many of them. And, it happens, and, the main problem with it is that you'll only realize down the line when you're trying to fix one thing or another. That's when you realize, oh, I don't really know where I created that variable, and then you spend a lot of time looking for it. Or you don't know if something is coming from the original data or from some change that you did to the data. This is why we recommend this workflow. Okay, another very good question. Is merging the same as making data wider? No, it is not. Although, yes, when you merge two data sets, technically they are becoming wider. When we talk about wide data and about reshapes in general, we discussed this in the book in chapter 5. What you are doing is you have one piece of data, one data table, and you are only changing what is displayed in a row versus what is displayed in a column. So you're only changing the format of the data, which is something that we classify as data cleaning. When you are merging two data sets, you are actually adding new data points. You are editing the content of the data set. So this is why we say this is part of construction. So making data wider generally means only changing the format, not the content. Okay, one more question. Does it then mean that when you append and or merge, you still retain the variables and units of observation, and they are just on the same plane or table? Yes, if I understand your question correctly, you are taking two different data tables and you are combining them either by row or by column. So you're either making, let's say, a vertical or a horizontal combination, but the information is still the same. This is the general principle. However, it is not exactly how all statistical software implement it. So for example, when you are appending two data sets, so you're putting them on top of each other, this may result in a lot of missing values being created. If, for example, the two data sets have a column with the same name in each of them that have different formats. So one of them is stored as text and the other one is stored as a number. When you combine them, you will lose information from one of the tables. And this is why harmonization is so important, because you may be losing information that you actually need and you did not intend to lose. So this is why it's so important, to keep in mind how many missings are created at any time that you do this. The same thing happens when merging. In R in particular, you have different commands to merge data sets. They're all part of the join family, but depending on whether you used a left join or a right join, you will lose observations if they are not in both data sets. And using a left join or a right join is what determines which observations you will lose. So this is, again, why we recommend making sure you understand what you want to do, and make sure that you check that this is actually what you have at the end of that process. What makes R a better software than, say, Stata? This is a very controversial question. You're assuming that R is better than Stata, which I like. But many of my colleagues here may not agree. They're different software, right? So first of all, Stata is a proprietary software and R is an open software. Stata is very specific to microeconometrics or econometrics in general, while R is the more general statistical language that can be used for a lot of different things. There's a lot more R users out there in the world than there are Stata users, but there are a lot more economists using Stata than R. I think personally that Stata is better that R is better if you want to do more complex things. It allows you a lot more flexibility than Stata does. However, there are still some econometric methods that are not implemented in R that are available in Stata. So I'll let Chris, Ben, jump in if you. I know you have a lot of thoughts about this. On R versus Stata. I like the way you approach the question. I'm more for R. Thank you. We actually did once in Dime, we did a debate and R won. At the end, the people watching the debate voted that R was better than Stata. Okay. Another question. While creating tables, what best practices determine variables that should be on row or column, text or numeric? I am not sure. I understand your question. So what will be displayed in a row or a column is entirely up to you. As you find your results, there will be a long process of thinking about what is the most compelling way to communicate these results to the public. And you often go through several iterations of the very same table, and you just find, different ways to organize it, and some are easier to read than others. So there's no one size fits all. Like, there's a lot of different things that you can do with the one table. What I would say, however, is that you'll always need text in both rows and columns to make sure your table is understandable. So at the very least, you will need column and row headers. And this is very important so that it's easy to see what each point in your table is representing. Dot is saying that she will have to learn coding to use all these things that you have taught us. Well, not necessarily. It depends a lot on what you are doing in your research project, right? So a research team can have people that do very different things. I do think it's important for everyone to have a sense of all these things that we discussed today. And this is why we included it on the book. However, there's a lot of, specialization of labor inside a research team. So a lot of people will be working on the research design and not necessarily be implementing the code. But you should still have a sense of what are coding tasks that come up so that you know how to organize your project. Yes, if you're working alone for a PhD and you are doing quantitative analysis, then I would say yes, I would recommend that you learn coding and that you implement your analysis using statistical software. I'll give you 1 more minute to send new questions, and then if no questions come in, then I'll just finish this. Thank you so much for bearing with us. Thank you. Okay, the 1 minute is over. Thank you everyone for coming in. And I unfortunately could not get to all the notes I had because I was too slow in this presentation, but everything that I wanted to mention is in the book. So please make sure that you read this chapter, and you can always ask us questions on Slack. We'll have our very last session for this course next week, when we'll talk about how to actually get our tables and graphs into a final document and get it published. See you next Thursday.